regarding
All right. So thank you.
Is it okay to record?
Yeah, it's fine.
Is it on?
So thank you for arranging this wonderful workshop at really nice place. So I spent a lot of time thinking about what should I talk about on Blackboard, which I haven't done for a long time. So then I realized there are a lot of experts in here, but still some people have a little bit of less touch on the instantons. As a soliton pipe physics, and also instanton string or self-real string in 6-dimensional superconfirmed theories and little string theories. So they have been playing an important role, and still people are very active in trying to understand their physics in 5D and 6D, and trying to employ their physics to understand 5D and 6D conformal field theories, and also little string theories. So those are very, very rich subjects, and there are a lot of ongoing researches. There are many experts in many of these topics, and I'll try to cover a small part of it, which we have been doing for the last 5 years, or almost. But I remember when I was undergraduate, some instantons started to get discovered, and then started to learn about it, and then instanton physics has been evolving for the last 30-40 years, and it's getting more and more sophisticated, and I feel like in the next 10 years, maybe it's pretty much will show up. Right, so, instantons, I'll talk about this, some sort of self-real configuration in Hamiltonian. In R4. So, and people have been studying this for a long time. And for example, if I think about SU2 variables, and then if one can characterize this instanton number by finding some index was some integer numbers with self-real probably positive integers, and that characterize this solitary configurations. And this solitary configuration is of block localized in say around the origin issues. And then this solitary configuration is a number of parameters.
Sorry, so you require that together with the equations of motion?
Oh, if this is satisfied, the equation of motion is satisfied automatically from the beyond.
Right.
So 8 times n, which is really 4 plus 4 times n. And of course, from here, very hard to solve it. But so if you want to think about single instantons, then it's this 8 general modes. This parameter means that you don't change the numbers, and actually it's the same as characterized by n. And then these 8 parameters characterize the configurations, and 4 of them is central mass position. So because it's like some block in 4-dimensional space-time, you can translate it in 4-dimensional space. And then there's 4 parameters, which is made of one which gives the scale of the theory. As a Yang-Mills theory in 4-dimensional, there is no scale at the theory. So this configuration can have an arbitrary size, which is scaling. And then you can have 3 parameters, which is the orientation. And you get the configuration is really S3 divided by C2. And so that's a single instanton. And if we have a, so this gives you sort of orientation of the configuration group space, non-abelian gauge. So it's non-abelian gauge theory, but like in ordinary QED case, when we go to spatial infinity, one can imagine some constant SU2 rotations, and this 3 indicates that constant rotation of the configurations. And now in 5D, super Yang theory, say n equal 1 or n equal 2, when I think about matter field, one can include matter field, then one can imagine Lagrangians, of course. 5D Yang theory with Yang coupling, whose dimension has coupling constant of dimension sometimes. And superconformability is the limit where G scale goes to infinity. So Yang coupling has this length scale, and this theory is non-linear, but before this theory as a physics on R1 plus 4 has instanton solitons. So if you look at the Newtonian density, it will be made of 4-dimensional action plus time component, electric field component, and then one has the phi sphere plus 3 del phi sphere. So that's the energy density, and one can see that there's a bounded energy coming from the this part. One can give a bound by using minus the sphere. So this usually gives us instanton bounded action or energy coming from instanton numbers. And the next one, these two component electric field and this scalar field can be combined into a single term, which is FU 0 minus d phi square plus and this covariant derivative on scalar field. Let's see, 5D Yang theory, n equal 1 supersymmetric Yang theory is made of the 5D field and 1 scalar field, which is imaginary reduction of the 6D n equal 1,0 Yang theory. So you have 1 scalar field, and so this part can be combined into a new covariant derivative. Can be taken out the straight. And then if you integrate over spatial direction, then it's a total derivative, then you can put it into bounded terms. Then this becomes electric field, electric charge of the 5D Yang field. So one ends up with bounded energy. And the V pi in SU2 will be 1f00 minus 1f. So V is the expectation value of scalar field, and the electric quantized electric charge has one with G scale in there.
Sorry, what is the symbol in front of Q?
Oh, V, which is the expectation value of scalar field. Spatial infinity. So you are breaking gauge symmetry from SU2 to U1 by scalar field phi, and so basically this integration of the density is bounded by instanton number plus electric charge. So this for n equal 1 case, n equal 2 case, we have more supersymmetry, and it allows to have an independent sum, and so energy is bounded by both Instanton number and electric charge. But if you have just n equal 1 supersymmetry, then there's only one line combination is allowed. Something similar to n equal 2 in Fortnite.
So do you require F0 equal to d mu phi?
Right. So PPS equation becomes F mu equal to F mu tilde, which is equation for instantons, and then d mu phi is equal to F mu 0, and then there's Gauss's law, and then there's d mu phi equal to 0, and then Gauss's law has to be both, which is 1 over 2 squared. But because d0 phi is equal to 0, and d mu f mu 0 is proportional to d mu phi, which means that its combined equation becomes d mu square phi is equal to 0. So there are two PPS equations. And because these instantons carry gauge symmetry is broken to it, so gauge symmetry S2 is broken to E1, and the instantons carry both electric charge, so they are called the ionic instantons. And this was first discussed by David Tom and Bill Lambert. So this, remember when I talked about instantons, I just talked about this, but now we have an additional equation, covariant Laplacian equation on this ordinate scalar field, which so the way we want to solve these problems, first solve the instanton problems, then on that background one solve the phi. And there it has a surprise, which is probably so for example, single instanton is simple, so two instantons. Solution in SU2 is called the Jacobi-Low-Levy solution. It's made of some harmonic functions in C and 5E and E. Okay, so those are most general two-instant solutions. For interesting thing about this two-instant solution is that as usual single instant two solution has this one in here, but Jacobi-Levy can lead to this constant into one, and that changes physics. And so if you look at the constant number of parameters, then it's more than, for two instantons, it's 4 times 2, or 8 times 2 is 16 parameters. But this one is more than 16 parameters. So, I mean, there are centrometers, but so it looks like this one is less, but this one is more than. But other things, so with that background, one can solve these Laplace equations.
Sorry, say that again. So how many parameters does this solution have?
Right, so counting says if I have number of instantons, then number of parameters is like 8 times n, which is
16.
16. 16 is made of the 4, which is centrometers position,
Yes.
plus 12. Okay. Now let's count this one. AI, there are 4 vectors, so there are 3 4 vectors, that's 12. Then SI, there are 3 of them, so 15. Then the overall scale probably you can take out then 14. So this one is 14 parameters.
I see.
And this, so instead of 12, we have 14 parameters. So there's some additional mathematical structure, and then right. So it sort of gives you.
Why is the center of mass centered?
Why?
The overall 4 that you subtracted from the 16, why isn't that part of the AIs then?
Right. I'm going too fast. There's some overall SU2 rotation. Right. So that you can take them into. So you want to count more carefully, go slowly. Right. 3 plus 12 is 9. So 3 is not taken care of, then this is 14 minus 4 is 10.
So it's one more.
One more, right.
I see. Not too bad.
Not too bad. Right. So AIs gives us 3 points, so let's put them on the plane. And then turns out, because now with this background, there's some SU2 rotation one can do. And then I choose scalar field to be. Then it turns out that this scalar profile, of course, it's constant. The orientation is fixed, but I can rotate this orientation instant with respect to this one because this is the zero mode of the solutions.
So, is there any physical intuition or something of why 2 instantons should have something like 3 singularities and not 2?
Right.
So you
Because the instanton is some sort of non-abelian block, and
so it's
right. So there's no position to see. It's just spread out some object. So obviously these 3 quantities. I think there's some. I used to think about this quite a lot on the old metric scale. So I think maybe constructively some torus there or all kinds of things happening, and some ellipsoid there. So, right, U1 parameters, they can rotate in this point in such a way, and they don't change the instantons. So now, interesting thing is, if you solve the covariant Laplace equation, then position where phi equal to 0, which is gauge invariant quantity, because phi equal to 0 is the phase symmetry is restored, and that's an interesting quantity. So you want to look at the paths. You want to look at those points. And those are very, very interesting. And so especially if, so let me draw those things. So as one changes, sometimes I can have a phi equal to 0 quantity like that. So, and sometimes it can go like this. So if you don't rotate U, then this trajectory where phi equal to 0 remain on the same plane as this 3 point. But if I rotate the U, then sometimes it comes out of it. So this orientation between this constant vacuum expectation value and instant orientation is also very important quantity characterization. And also, right, so you don't see any of this. Why this is like that?
I'm getting a little lost here. You're drawing 3 copies of the positions of the AIs, and those closed curves are the locus of
phi equal to 0.
Phi equal to 0.
And I'm changing the parameter SI. And
what's the difference between? I can see in one case there's 2 separate guys.
Right. So if I make a ST very, very small, then you are sometimes you are localizing instantons, and you end up with 2 instantons. But if I make instanton, each of instanton to be getting bigger, then they merge into single piece, and then
So these 3 pictures is supposed to be like a movie.
right. It's a movie, right. As I change the parameter as well as I see. And also, if I change the U, which I cannot do, then these lines comes out and get bended around. So this, so let's go back to the brain pictures. So this I'm just recording, but so let's look at the 2 D4 brains on which there's 5 view and 2 super images.
Sorry.
Yeah.
Sorry about that. So that phi over there, right?
Yeah.
So is that the scalar field
Right.
on the left, and then the 3 crosses are the 3 locations AI, A1, A2, A3,
Right.
and the lines you drew are the locus of phi x equals 0.
Right.
So I see. And then
And so for sort of large SI scale parameters,
They
it's kind
don't.
of 1 log, but then they break up
Right.
into small
I
SI.
see. So
it
the,
looks like
the SIs are very large.
It's not, there's no clear.
No, so you can imagine one of them to be like one to be like this. So let's say then you make S1 and A1 goes to infinity.
Right.
And then if this ratio becomes 1, then it becomes like 2 solution, so 2
Right.
instantaneous. Then you can see something like that.
So I see. But in general, it's more.
Right, it's still, right.
Thank you.
So depending on which one choose, this can go to there or there.
Yes.
So from brain picture, so here is 2 D4 brain separated by V, because I took the expectation value like that. And V equals to 0, phi, this is like a coordinate phi, and phi equals to 0 is very clear physical distinct point. And then instantons, we know is made of the digital brains. So here's digital brains, and then here is fundamental strings connecting to digital brains. Now, interesting thing is, if you look at the energy, and if I look at the instant numbers and the electric charge to be positive, then there is no force between them. The energy is just sum of them. So there is no force between the electric charge and instant numbers. So they can go away, and they can put them together, or something like that. So there is a fundamental string and digital brains. They don't kill each other. You can put them together, stuff like that. But from this instant configuration, you can see that as you put them together and spread the instantons, something interesting is happening. So this is very similar to monopole case. If we have monopole D1 string, then if we have DC, then there is a kind of effect where DC brains are banded and connected by D1 strings. But here we have fundamental string and digital brains. Then they are putting together these 4 brains and putting into this same shape. So this circle trajectory coming down. So let me draw this case. That's the one. There are two T4 brains are coming together into some circle. And along the circle, there is a fundamental string, and then digital brains are sprinkled along all these circuits. And one can understand this one as a bias effect. There's a bias effect. So this basically D2 brain dipole is induced. And so there's some sort of, so if I think about D4 brains, Can you imagine there's a deep brain connecting them, which is called the monopoly string. And this loop of monopoly strings are voided due to the presence of digit and fundamental string. So this locus where phi equals to 0 is the loop of deep brain. And those are called
Yeah, the basic question.
yeah.
So when we think about DP plus 4 system, with instantons, we should think of them as point instantons, right?
Yeah.
Moving in this correlation
Right.
of this thing. But when you have a non-trivial wave, the phi turned down,
Right.
can you still think of them as point instantons?
Depending on what
In
issue
the
you're
default,
looking at. Right, so in symmetric phase, there's instant moduli space and so on. But if I go to Coulomb phase, of course, they become U1 instanton, so which is like point line. But somehow, when I put an electric charge, it blows up. So without electric charge, if there's nothing to connect the two different brains, then digital brain will be just like point like out there. But if I add a quantum string, then they combine together into this this tube of monopole strings. And this is called super tube. Of Thomson. Now, interesting thing is that if you look at the deep zero brain on deep brain, then there's like a magnetic flux. And fundamental string is like electrically charged electric field. Then E cross B gives a momentum, so there is momentum flowing. So in each along the tube, there is some momentum flowing. So these dionic instantons carry angular momentum naturally. So those are people having a lot of fun. And the amount, classically, maximum amount of angular momentum is carried by this round shape, and is proportional to instanton number times q, square root 2. So as I have a single instanton, so instantons, then it doesn't carry any angular momentum. By electric charge particle, there's W boson carries bit of it, but it doesn't carry any momentum. But when I put them together, depending on the shapes, it can carry a lot of angular momentum.
Can you explain more about how different brains are used?
How do these brains are? Oh, well, there are many ways.
We started from people brains, D0 brains, and fundamental strings.
So I solved the covariant Laplace equation, and then if you connecting these two, then this is a D2 brain, because this line comes out. So this line constitutes two different brains. So now you have these things, then you ask, how do you count them, quantum mechanical?
And the fact that J goes like a square root of Q can be understood by looking that the energy goes like J squared.
Right. So how do you characterize the quantum, how do you count them? That's the Laplace of partition function. So to count this quantity is object. So now you have some clear pictures about dionic instanton in 5D n equal 1 or n equal 2 gauge series in Coulomb phase. So those are like combined object which carries both electric and magnetic charge and angular momentum. So this is very strange soliton kind of thing we don't put here. So one wants to count number of such a state quantum mechanical. So there are many supercharges in physics, but one just choose one supercharge. So R4 has SO4 index, which is made of SO4 is made of. So there's R1 plus R4, but this rotational symmetry is SO4, which is made of SU2 plus SU2, and you see minus plus. And give an index alpha alpha. And then there is SU2 R symmetries. give you index A, and if it's n equal 2, then there's S5, arithmetic goes to SP2, and then there's SP2 one more, and that's called A. And so that's the index the one gives, and we are interested in choosing one of the, finally, formulas satisfy similar environmental conditions. But you choose one of these supercharges, say Q1.2, and then you set up the index, written index in 5D Young theory. So you are counting state with satisfy some p-test bound. So roughly Q space like the instanton number minus electric charge with some units. And then, because you just choose one supercharge, there are many additional global symmetry which comes with this supercharge. So one can add the chemical potential for that. So this index, in if A equal 2, there is an index for A, and this SG2 rotation of this arithmetic gives less than chemical potential M, and this one special rotation which is not combined together. This one has chemical potential epsilon minus, combined one has epsilon plus. So one can set up the index for a given supercharge.
So what is the second Q square equals H minus I minus what?
Q is equal to H minus I minus Q. But this is electric charge, sorry. So PPS means they are equal. So energy is given to instant number plus electric charge. And then for given charge, supercharge, because this is independent bar, one can introduce chemical potential for this carton of this SG2 minus. And also there's if your supersymmetry is equal to 4 and equal to 2, then you can introduce additional chemical potential. If you have more flavors with equals, then one can introduce more chemical potential for flavor switches and so on.
So M is the adjoint mass of it.
M is right, adjoint mass, right. And then secretly also instant number is commuting, so you can introduce the chemical potential for instant numbers. But as we know, 5 Young is incomplete. So one cannot calculate this directly because so there's trick to do that. So you split the calculation into two pieces. One coming from there's portability part. So because we are calculating this in condition is one has to come to this Coulomb part. So if we have many higher rank gauge group, there are many chemical potential for which counts the electric charge of each carton of the non-abelian group. So one has to count that, then one has to count the instant numbers. So those are basically index within index for this kind of object in general gauge group. Right, so, but field theoretically is extremely hard calculation to do, And so the trick is to split this calculation into two pieces. So it's made of automotive, for example, if because I'm thinking about broken symmetry, so if I have electric charge, W boson by itself is EPS, and those are automotive objects, so I include those things, which is there without any instantons. There will be automotive part of contributions, then there will be contribution from instantons, which is made of one, when there is no instanton, then contribution from n instant contributions.
Does it start with one, or does it start with higher powers of Q? Or is it not Q?
Oh, you mean Q is the chemical potential for instantons? So
Yeah.
zero instanton should be one because the rest of field theory contribution is given in terms of automotive parts.
Oh, so Zn can start with some higher power.
Right.
Okay, I see.
Right, so so whole Z or I is made of 3 automotive times 1 plus this instant contribution. So this part you can do it calculated using 5D analysis. Now, instant part, instead of doing 5D analysis, you do ADHM quantum mechanics. So excuse is that, especially if you have flavors and so on, then theory is not well defined in short distance, and the ADHM quantum mechanics gives you completion of the theory.
But that's for ordinary instantons, right? Not dionic instantons. I mean, that description is for ordinary instantons, not dionic instantons, right?
Ordinary instanton is ADHM, matrix models. But when you include ADHM quantum mechanics, dynamics of the ADHM variables, then it has dynamic contribution also. So this one has electric charge in there. So, right, so there is an electric charge part over here. Then again, this one, if I expand it, then there will be pure instanton contribution plus 1 electric charge, 2 electric charge, and so on. So it's quite a mixed bag.
So you can write a closed form for Zn,
Yeah,
including the
electric charge. Right. That's what makes it things complicated.
and does it have any description in terms of what I mean? So there was an original matrix model, right?
Right.
Because the one volume theory
Right.
was easier, right?
So
can it, I mean, is it like some decorated form?
right, exactly. So it's basically dynamics of digital brains with some, if we have flavor, then there's another, say, D6 brains or D8 brains, then it gives a flavor symmetry. So basically we are writing down dynamics of digital brains, which is the dynamics of ADHM, so quantum mechanics.
Oh no, I just meant that addition of electric charges.
Right.
What does it?
It will be sort of global symmetry of the ADHM quantum mechanics. Okay. Maybe I can hear that. Now, when we have multiple D4 brains, so transpose section is 5 million, so suppose we start with D4 brains, so this is say 5 and 6 sections, and then if I think about adding one more D4 brain, then I can think about fundamental strings and the digital brains and so on. But if I put another D4 brain not along the parallel direction and connect the diamonds of fundamental string connecting these two D4 brains, and they are not mutually BPS. really they are repulsive to each other, and these two fundamental strings are pushed away from each other. So this is not a nice system to think about. So rather one think about just turning on one scalar field, so all along the. So you just in two cases there are 5 scalar fields, and one just choose one scalar field expectation value. And then one set of ADH quantum mechanics, and chemical index in ADH quantum mechanics, which gives you index for the object, this varying instantaneous. So ADH quantum mechanics describes if we have k instantons, then it's a k video range. So k is bk. So there is bk field with consonant formulas, and then there is a scalar, like this hypermultiple. This vector, which tells the position of the instantons.
Is this 0 for quantum mechanics?
Right, this is 0 for quantum mechanics. So later on I'll lift to 1 plus 1 with field theory, but and this, you know the supercharges. One was more or less same supercharge, and then phi alpha naught is like 4 vectors in the R4, so it gives you position of the instantons, and then one has number alpha A. And then this position and this parameter transpose position. So you can take away digital plane away from D4 planes. So this will be n equal to finally n equal to case. A, that's the. And then and then one has contribution from string connecting digital plane to D4 version, which is another hyper, 2 alpha, psi, and that's it. And this is those are UK ordering. And this is UK procedure and so this bifundamental method field knows about the global symmetry of the broken gauge group, and this amount of this global charge will count for the electric charge of the instantons.
But you had an adjoint mass there, so you probably.
Adjoint mass comes from the technical potential 4.
Yeah, right.
Is hypermultiple.
So you probably have the free content of 4,4.
Right, indeed, it's 4,4. But later when we put the flavors and so on.
Right, generally.
Right. So one set of the index more or less same index on that quantum mechanics, but then now you are in the sector where something is number is fixed, and so you take a trace on these instantons, and so Q square on instant pink dynamics will be like do you have a 5D BTS condition of the energy is made of instanton number plus electric charge, but you are doing BTS in given instanton number, then energy is just given in terms of electric charge. That's the BTS condition. Then you add the additional chemical potential. Now this quantum mechanics passing in Euclidean time. So this can be done quite straightforward way. There's nothing magical about it. Only thing from the previous thing is because of the Hamiltonian, ordinary Hamiltonian is shifted, and also there's additional quantities. So end result is one shift. If we go to Euclidean passing theorem, then shifting of the Hamiltonian by electric charge or this constant quantity is sensitive about, for example, if I think about, say, two-dimensional quantum mechanics, or suppose we turn on the chemical potential along the angular momentum. Plus px x dot plus py y dot. Then when we integrate over px, this is shifting time derivative by, so if I integrate over px, then you can see px is made of x dot minus plus y u1. Okay? So you are shifting time derivative operated by some quantity. That's what this additional chemical potential is doing. So you can do it quite straightforward. You can all that, and what it does is basically is shifting ordinary covariant derivative of the field, which is UK fundamental or UK adjoint, or you are shifting covariant derivative in a manner. So you are just shifting ordinary derivative by some quantity which is sensitive about the constant quantities. So that's very strange of writing down Euclidean passing theorem, because you have now some sort of charge operator in front of this covariant derivative. So once you have that, you have passing theorem, and your Hamiltonian has been changed. So you, and then you are doing index. So sometimes you want to change the supercharge also in this manner. Okay, so you have all, this will be like a new kind of supercharge, a new kind of index for given supercharge. Then you are doing passing theorem using stationary passing theorem. So with this, then which include, for example, gauge fixing, PRST, and all that, plus all there's whole industry to develop how to calculate the this. But basically, the thing is, this K-distance partition function is made of so stationary point, and then if there's some variation, there's a stationary point variation times one loop. That's these famous localizations. So that's there are a lot of references where they work out this detail of this. so I guess it took quite a while for the class to develop it, then it took quite a while for this technology to be spread, and I guess we acquired it about 7 years ago, and we have been using it quite often. Right. So that's the basically. There are a lot of mathematics in there, but one can do quite straightforward passing data and look at the stationary point and look at some of the contributions. So let's look at the U1 case. So it's 5D Yang theory with U1 gauge looks like a free, but one can turn the FI terms. And then space becomes a bit fuzzy, and the instanton point like instanton becomes blown up. And so K instantons has 4K variables. Each instanton, even though it's broader, only parameter it has is just position in R4, and they are wandering around. And it has a finite size given in terms of, roughly given in terms of size of the finite terms. And then single instantons. Let me write down this. So that's the answer for
Is this what you were calling Z?
Z1, sorry, Z and I. Right, so that's the partition function or index for single instanton. So this looks like awfully complicated.
So it will depend on the electric charge.
Right, because of single instanton. And the gauge looks U1, so there's nothing, no fundamental string. But still, this one has a very interesting physics in there.
So in this case, the moduli space is just R4.
Yeah, R4.
This is like a single.
Right, so it will be R4 K divided by SK, because they are all identical particles.
Perhaps they're not the same.
Hmm?
Or perhaps they're not the same. But so this is just like a chiral multiplet and a Fermi multiplet for
Right.
in the quantum mechanics.
Well, right, because you are theory, I erased it, but right, so basically this Q is the contributor in the calculation, and the vector in the, they are all free, non-interacting way. Right, so this looks like, it turns out one can calculate the total speed. One can calculate all n instantons, which I will give you answer soon. For two instantons, there are two stationary points. Single instantons, there is no stationary point. There is one stationary point where everything is equal to 0. For two instantons, but this one has also contribution from the this free, for example, U1 alternative particle, because basically there is a epsilon 1 and epsilon 2 is omega deformation on the 1-2 plane and the 3-4 planes. And so this partition function has a simple pole at epsilon 1 and epsilon 2. Basically, this camera potential is, there are many ways of looking at it, is deforming the geometry and almost like putting the harmonic well at the origin. And so there's, if this epsilon 1 and epsilon 2 defines that quantity, so there's a simple pole, and this comes from this phi alpha alpha, which is position of the instantons. Now, two instantons is they are made of two pieces of station point, which is characterized by two Young diagrams. And the way why on earth you have Young diagram is that when you have two identical particles, some sense we are doing supersymmetric objects, so we are doing some holomorphic type of thing. So when I put two instantons, I can either put them on the, say, remember this is C2. So this one is like the, this is like epsilon 1 omega deformation, this is like epsilon 2 omega deformation. It's like 1-to plane or 3-to plane stacking kind of. So when you stack them, two identical particles, either you can stack on the 1-to plane or 3-to planes. So that's kind of
there is also the contribution when you have like 1 plus 1 as well, right? Yeah.
1 plus 1, oh.
Box plus box also, right?
No, that will be, when you do calculate that, this one includes that part of it. So which I'll tell you. So, two instantons, so it turns out I2 like you put that this gauge group is U2, so you have to integrate over quantum mechanics. There are vector contributions, hyper contributions, and bifundamental contributions. Then you have to integrate over. And fortunately, you don't need to integrate. People have done it already. And there's explicit expression for each of the contributions, and then you put them together. And then there are many poles like this, double poles. Then there's spurious poles, which you disappear when you combine them together. And after a lot of song and dance, one can show this is true. And turns out, one can calculate this quantity using topological string calculations or in instanton dynamics. Sometimes one is better than others and so on. So this instanton contribution one can exponentiate them. And then you can put into persist form. So that's the whole partition function. So in UR theory, there's no Doppler bosons, massive charge particle at the rest, so there's no perturbative correction. So this is the whole partition function. And it turns out that n equal 2 theory, 5D n equal 2 theory is 62 model theory. And that's physics on N and pi branes. So this physics captures the physics of single and pi brane. So and n-pi brane, single n-pi brane, we know there's a variant tensor multiply.
Sorry, since you are equating a 5-dimensional theory to a 6-dimensional theory, could you say a few words about that sign?
Right, so n-pi branes, if we wrap on a circle, then it becomes D4 branes. So physics of n-pi brane on a circle is D4 brane. Between n-pi branes, we have M2 branes, can connect them, n-pi. Can have M2 branes, and if we wrap the M2 brane on a circle together, it becomes W boson.
So it's the statement that 62,0 on a circle is equivalent to phi d, with where the coupling constant is related to the radius of the circles and so on.
It's not clear that that's true.
Yeah, it's not clear that that's true.
It says it flows to it in some sense.
You're
saying that it flows to the phi d and equals to. In other words, it's not clear that the.
Oh, right. So let me.
What do you mean by the?
So let me tell you a little more. That 5D Yang-Lee theory has on n equal to Yang-Lee theory has coupling constant, which is the landscape. So. And then actually it's 1 square over square. Right, so Simon, I think, has proposed that this theory, it looks like non-normalizable and incomplete, but in strong coupling limit, means G square goes to infinite limit, is the 62 model theory. That was a proposal more elaborated by Michael Douglas and Lee Lambert and so on. So, and also the key observation was the instantons. Klein mode. So usually if we study 60 theory and then go to small radius limit, and then we throw it away Klein mode, and then we end up with 5D Yang-Lee theory. But somehow 5D Yang-Lee theory is an instanton, and they secretly know about Klein modes, and yeah.
It might not be that these series are equal, but it might be that they're equal for the purpose of computing protected BPS quantities.
So these things will not contribute to.
I think there's a difference between these two things.
Oh yeah, there are some difference. What it means is that because when I suppose think about the D5 branes and M5 branes, and in the limit where we are looking at physics, we are gravitatively coupled, and if we think of wrapping M5 brane in a circle, there is a D4 brane. So D4 brane physics may not capture complete physics of M5 branes. There may be more, but it captures quite a big chunk of it. Right.
Yes, certainly if you compute any non-protected quantity.
And people have computed non-protected quantities, and this is not great.
Oh, you mean like
scattering amplitudes and photons. I think
well, but I know the 4-point interaction gives the same answer. That's the what F to the fourth term. This work by C, not the 2 level. One more gives the answer of the 60. So what C and other guys did was, suppose I go to Coulomb phase of M5 branes, and then there's tensor multiple coming in, and then they go from Bravo M2 branes, and then going out. So there's some scattering of the tensor multiples. And I think I can really talk about it next week, a little more about it. And then one can calculate this exactly using conformance matrix.
So it's the statement that even at one loop, This.
5 Yang theory calculation. Of course, it's again BPS subject. It turns out.
Well, no, the 4-point function, even if the 4 external states are BPS, the 4-point function is not.
No, so it turns out this effective action.
Oh, I see.
This is a BPS object. And this gives you exactly the right answer. And one can reproduce this from 5D calculations again. So whenever you do BPS, you get it right.
Yeah.
Whenever you don't, then. Right, so I'm saying that 5D Yang theory N equals 2 series may be not incomplete, but question remains how do we make it complete such a way that it captures all the 62 common theory, which is unknown.
I mean, there are, in principle, several UV completions of the 5D super. Well, probably not infinite, but I think of at least 2. It's probably more. So, yeah.
You have this really embedded.
There are various different ways that you can embed in string theory. I mean, the dimensional reduction of 1 super Yang mills in 6 dimensions also gives you 5D Yang mills, 2 super Yang mills. 1 super Yang mills in 6 dimensions isn't UV complete, but it can be completed in string theory.
Right.
So that's already 2, right? And we haven't tried very hard.
No, right, there are a lot more. Right, okay, so, but our joy doesn't stop there. So
Maybe it's a good time for having the coffee break.
okay,
What do you think?
then I'll come back. There's more instantons than instanton strings. And one can explain this impression by thinking about Kimyeong and fibers. So rather, let's think about 61 component states. Then there are 3 kinds of multiples. So we put some. So we are focusing on some of the supercharges. It's more complicated to have just writing down one expression. There's a tensor, and that tensor is going to. And one can think about BPS. So because we are thinking about theory on, when we think about 60 series, we are thinking about theory on R circle compactified series. So you are compactifying one of those spatial directions, and then you are looking at the physics of it, and then you are looking at BPS sound pattern. Most natural thing in 60, because this multiples, when you think about just single multiplet, they are all merciless, so they are BPS when they are moving with the speed of light. And so, moving with speed of light along the circle. So one has a circle momentum, chemical potential for circle momentum to be Q, and then using omega deformations and all that, index for each of vector tensor hyper is given in terms of this single letter index. This expression. So then we write down tensor contribution is minus T. So roughly with the different unit, T is like epsilon minus epsilon plus, and U is like epsilon minus epsilon minus, and this is like 4 at epsilon 1, and this is 4 at epsilon 2. So basically, one can express it in terms of synchrony functions. It's below it. Then one can show this is basically characteristic exponent of the tensor plus hyper. Because two-comma theory in 6D is made of the tensor and hyper. So basically, all which tells us that we know that single M5 brane wrapping on a circle, then momentum along the circle is D0 branes. So instanton physics is capturing the Cartesian mode, and all this index partition function of this Cartesian mode can be just captured by quantitative expression of this tensor multiple plus hyper. So it captures pretty much 60 M5 brane physics. So that's for U1. Let's look at that U2. Then, of course, things get much more complicated. The biggest stationary point is made of two colored Young units. Suppose if I have instanton number K is made of K1 plus K2, and I have two Young diagrams. So if we have D4 branes, two D4 branes, and here's the Young diagram on the top, then there's another Young diagram at the bottom. So it's made of two Young diagrams. Then you have to sum of the Young diagrams. So instanton partition function is made of but Gn is made of sum of Young diagrams. Okay. Sum of Young diagrams, Y1. So Y1, right? Y1, right? So you have, for each Young diagram, you have expression, which is given in the very long expression. You can get any standard reference, and this form is given. Then you sum of all Young diagrams, whose total number is given in terms of total number. And then, as I said again, each expression is given in terms of synchrony function with poles, with multiple poles, including poles where Coulomb, now this will depend on Coulomb, not only it will depend on Coulomb parameters and so on. And you could have a pole. Remember, if we have SU2 instantons, this omega deformation parameter is in a way to remove the zero mode. So if we have instanton, then its position can be any place in our pole. And epsilon 1, epsilon 2, omega deformation push them to the origin. Now, instanton can have any scales. If the electric charge, then instanton scale blows up. But this, when you turn on the chemical potential along the cardinal of the gauge group, that's the one which pushes the instanton scale to the origin. Okay, so there is a pole whenever you turn up this chemical potential. So there are poles, for example, two epsilon plus. These sort of poles are there. So there are a lot of spurious forms also. They all combine together into this sphere. So Young diagram in some sense is like somebody asked me to summarize the calculus in a single word as a divide and conquer. So this problem of counting is again very difficult. You divide into problem to Young diagrams, then you can calculate each of them, then you combine them together, then each expression has a redundant information which will disappear. But on the other hand, each expression is made of expressions. Right. So one can calculate, but as you see, one can calculate and so on. But key, there are many information in there. One of key information I want to emphasize before going to other problem is that you can have additional quantum. So there are additional quantum state which is not obvious from the ordinary field theoretic point of view. So suppose we have D4, or from 64 to 85. And let's connect them fundamental string. I can have 2 fundamental string, W boson 1, 2, 3, or 1, 3, or 2, 3. So let's think about W boson which goes from 1 to 3. Even though it's on the same line, there is a possibility of splitting this one into 1 to 3. So this W string, W boson or fundamental string doesn't know what D4. That's a quantum state. And then let's put a D0 in here, or instanton. Because this U1 instanton D4, this one wouldn't know about presence of this, but turns out they can have this threshold bound state. So that gives you sort of additional quantum state. When you calculate this very complicated way, then you realize that those are something novel about it. From point of M5 rays, this 1, 3, W boson is M2 plane connecting first and third M5 rays. But this M2 plane can carry momentum along the 2 directions. Even though it has to go through and not knowing, but somehow it managed to carry the momentum on the 2 directions. And the way I imagine that is possible is because you can open up like this. Some sort of threshold bounce. Open up, of course, that doesn't make it to be BPS. However, if you open up and move this one is the speed of light, then that's BPS. And
I'm not trying to understand the picture.
So here's M5 plane, and then there's 2 M5, so it's M2 plane connecting these 2.
Right.
But along the way, I open up, of course, general bit along the M5 plane, so I open up time bit of it.
But it has a narrow tube touching.
Right. But this, of course, they will not be BPS. But if it's moving with the speed of light, then that's BPS. So that it can be translated to additional 0.4. Or additional quantum state. And this turns out to be crucial in counting the n-cubic degrees of freedom. And basically, so one can calculate this using either elliptic genus calculation of 60 or one can do it with instanton dynamics. They match each other exactly. And also this elliptic genus calculation of this can be TDLI, and Sublim has shown brilliantly that leading degrees of freedom BPS counting goes over n cubed. So we think there are n cubic degrees of BPS state. Remember, M5 brane, if we do turn on the heat and the counter entropy, the entropy increases with n cube. And also anomaly polynomials, if you hit the M5 brane with external gauge field, then it responds with like n cubic degrees of freedom. And also which has been shown by Kim and his collaborators, that if you count the BPS and go to large momentum ready, then you can do the SCFT transformation and immediately it has n cubic degrees of freedom. So there are many ways of understanding n cubic degrees of freedom, and many calculations shows that. Right. So now let's go to n equal 1 theory, which is the more flavors, which we heard a little bit from the Army High. So do you have any more question about this 2,0 series and n equal to 5B series? We can a little bit more about So let's think about n equal 1, let's see 2. But I'm not trying to repeat what has been known, but I'm trying to bring the viewpoint to the whole story. So Cyborg has shown that in strong quantum limit, there's a 5D supercomponent theory with enhanced global symmetry, which is n+1, and E+1, and this U1 coming from the instant numbers. Now one can show that either using instant partition function on S1 cross index functions, or LE and the others has shown that the class of partition function, this one has with some clever trick, this partition function, when you expand it right, this one has also EN global symmetry. And so let me show how, let me just write down the answer. So again, with this setup, one can calculate the index on R1 plus R4. So when we set up the index, we do it in Minkowski time, right? We are tracing over all particle state with certain weight. And then we translate that to Euclidean time integrations, and then we calculate. Again, this is made of the G topology, plus 1 plus instant contributions. Now, useful thing is exponential integral and putting it into plastic form, about which Anya told us so much. When he talked about all this, I was, what is this? For a long time, then gradually it became part of my tool too. So what we heard today about Higgs mechanism and so on, what is this? Then a few years, then it become my tool. Now this Fs, single particle, this can be expressed in a very interesting way. There are many notations, and I use notation which is non-standard, but something more useful to think about. And this number is called Kopakuma value. And this F is basically a quantity which tells about the angular momentum of the ionic PPS subject. Remember, in four-dimensional, angular SO4 is made of SU2 cos SU2, and J left and J right is this pattern of the two SU2s. So this one is a nice expression. But also it knows about pole structures. So that's basically tells about angular momentum of the PPS subject, and this one tells about electric charge of the object. So there'll be charge 1, charge 2, charge 0, and all this state. And if you have a multiple gauge group, then there'll be a counting for each of the cartons. And then this one tells about the number of PPS that belong to given charge and given angular momentum. So this sort of Kopakuman invariant is the one which counts the PPS object, PPS state of this dielectric instantons. Now, so you can, because whole thing is made of pathologic and instanton contributions, you can just look at the vector multiplies and hypermultiplies in Coulomb phase, and then do the pathologic part of this free energy contributions and see what happens. And then you can see that hypermultiply gives you F0, where J1 is J0, J left and J right, and if you put hypermultiply and then put it into exponent, and then you can see this is the right quantity with the electric charge contributions in there, which I'm telling you more. Now, W boson, SW boson gives you F0, F1. Now, I said this, remember when we talked about SU2 case, there was Coulomb parameters. This kind of form, and e to the plus minus 2 pi I u is like, minus I u is like chemical potential for electric charge. But when you expand, say, let's look at SU2 with NF flavors, then natural expression for expansion is not this Coulomb modular parameter A, whether something called A theta is e to the minus theta u or A times Q fractional number of instantons. And it turns out from PQ fiber and web of the fiber conformal field theory, this expression is very natural part of the expression. With that, for example, NF equal to 5, when there's 5 flavors, in S the global symmetry is from SO 10 cos U1 is in S to the E6, and this single particle index goes to 0. Pi 27 bar over E6 theta. So there's a 8 theta square cubic, and the electric charge is increasing as in this part. And the first expression is with a single electric charge. Funny thing is that there's hypermultiply contribution. So this field is made of both perturbative part and instanton, two single and two instanton. So one can show this is made of 10. And the vector multiplicative part, this is made of 1 plus 61 plus 10. So one can see really interesting. What I want to say is that this SG2 gauge theory, so I went to Coulomb phase and I went, but instead of, so we have SG2 description, but we go to infinite coupling limit, then we are in Coulomb conformal field theory. Now again, I can go to Coulomb phase and I ask myself how many W bosons I have, because SG2 is broken to U1, there should be only one, but turns out there are 27 of them. So I could have chosen any one of them to be my W bosons, and then there are 27 ways of SG2 for this theory. So same for hypermultiplet. I have 10 hypermultiplet, but the instanton, single and two instanton combined together into the 27 hypermultiplets. So some of them will be perturbative, some of them will be non-perturbative. And usually instanton doesn't generate any additional vector multiplet in SG2 gauge theory because flavor symmetry just doesn't provide a spin from fermionic zero mode. Turns out this pole structure tells you that which pole structure gives an expand, gives the electric charge square, which tells that this instanton you have to really expand it, then re-express it, not just a fermionic zero mode, but hypermultiplet from the this bifundamental multifield, which gives the denominator bosonic part we put it together, then generate this additional vector multiplies. So this very same duality in this deformed way, there's one W bosons, but theory has 27 vector bosons. And we choose one of them to be W boson, rest of them comes from instanton and two instantons. So this is a very different way of looking at Hawk-Moore invariant. Right. And in 5D theories, there are a lot more to be done. As recently, new kind of 5D superconformal field theories has been discovered, and also new kind of 5D construct, non-Lagrangian theory has been constructed for some of the 60 conformal field theories. So that's the 5D story. So let me go to 6D story briefly, then end. So instantons are solitons in 5D physics, and it has extremely rich characters, and not all of it is known, as we can think about, say, non-classical gauge groups, then we don't have ADHM technology, or if we think of SOM gauge group with some spinometers, then again one needs additional technology to take care of those spinometers into the instanton dynamics, and so on. In 6D series, there's a superconformal series and interesting series. And the instantons play an important role in both sides. And so let me just focus on just one problem, just to be simple about it. So let's think about interesting series, because it has part of it is superconformal series. So let's think about N and as 5 minutes. To A or to B, exploring T 4 plus R there. We want these two theories, type 2A and type 2B, these things are T2 to each other, and I've been writing recently we finished the paper with Juno Kim, with you. And So basically, from 2A perspective, it's basically same as putting a O6 brane with multiple D6 branes, and then you sprinkle them with NS5 branes. And if I have single NS5 branes, then it gets split into half NS5 brane, about which I again showed maybe 15 years ago. I've been digesting these papers. And inside there's O6 plus and outside O6 minus. And here is SPR, KG group, coupled this tensor. There's SO2R plus 8 theories. And in 6D theories, let's think about this theory. Then it's the 61 supercomposite theories. And as even though I didn't mention it, formulas in vector multiplet has opposite chirality from hypermultiplets and tensor multiplets. And so if we think about SPR gauge theory in 6D, then just as pure gauge theory is anomalous because its gauge inner field has a single chirality. On the other hand, if you have a metal multiple 500 metals, then it gives additional contributions in a way that there's when you have anomaly calculated for the gauge inner field, then there's a trace F to the fourth, which is related to trace F to the fourth fundamental representation with a 2n, I think, plus minus 8, plus 8 for SPR. And then this multiple is 500 method contribution cancels this because of the hypermultiplet has an opposite chirality from the gauge chirality. So method contributes. So trace that the fourth term cancels because of this flavors matrix. On the other hand, there's part. This can be cancelled only when you couple tensor multiplet to gauge multiplet in a way that H is given in terms of dB plus minus square root of CR, Chern-Simons terms, and then additional coupling between dB and CR is basically contribution to there's vector contribution and hyper contribution, then sum is CR. So you have anomalous contribution to this anomaly polynomial coming from vector contributions and hypermultiplets, and that part can be cancelled by Green-Schwarz mechanism by coupling tensor multiplet to the vector multiplet. There's an additional bit where the effective coupling for the Yang-Lee theory comes from scalar of the tensor. So in tensor range, one has effective coupling constant, and when tensor scalar has zero expectation value, it becomes very strongly interacting. So this tensor multiplet expectation value is a separation between two half NS fibrils, and conformal limit will be where these two half NS fibrils come together. Right. So here again, one can think about the Instanton string of this SPR gauge group, which is given in terms of gauge groups SPR, then the Instanton string dynamics will be given by OK group. OK group is made of two pieces. OK plus and then OK minus. OK plus is the element whose determinant is 1, so it's SOK, and OK minus is the element whose determinant is -1. So which sometimes and you can turn on because we are calculating the partition function of T2, you can turn on the holonomy on the both sides in different way. This could be OK, this could be plus and OK minus, and so it's very complicated holonomy groups, and so it is sophisticated path integral on dynamics of this instanton strings, whose schema theory can be written down rather straightforward way. So, for example, so there's fundamental multiplet related to this global symmetry, then there's gauge symmetry, SPR, then OK, there's 5 fundamental vector field, then there's OK symmetric representation, hypermultiple, which tells about instant position, string position on this four-dimensional space, like this instant position. Then one can do the elliptic genus calculation and then do the integration using Jeffrey Cohen method.
We need 2 copies of SO2 plus.
Oh, right, because I know this. Right, so they combine into S4R plus 16. So one can calculate it, especially when R equals to 0. SP0 case turns out this together it becomes SO16, and when R equals to 0, this leads to EA string. Where SO16 global symmetry is enhanced to EA. And this is a very interesting direction to explore. But other direction we've been doing is merging 2 ends together. So this gives us before that, this is unfortunately with SPR, and from which one can calculate the partition function. Again, the totality plus 1 plus sum over now instant y numbers. So one can calculate this partition function. Each one of them is given in terms of elliptic genus. And then there's lots of properties, like as a 60 theory, there can be some global anomalies with respect to world volume gravitons or transverse gravitons, which give us the inflow mechanism for anomalies on these self-drive strings, which leads to the which give us how either depending on various parameters like H1 and H2 and other parameters through holonomy anomaly equations. And so there's a lot of structures in there. One can calculate directly, then explore the structures, put them together, and for example, when R equals to 0, one can show that this Kopakonoma invariant has EA global symmetries and so on. And also, one can combine them together into little strings by compactifying this transverse difference, and then one can test the T-dualities. So let me draw the simple diagrams. Here's the SPR theory, and there's slow 2R plus 8 series. And turns out this is a theory of the NS5 and type 2A theory exploring DR plus 4 type of singularity. And then 2B picture, if we have NS5 exploring DR plus 4 type of singularity, we can SQL it, and it's like a D5 range exploring. So aware that one has this schema theory. There are of course none of them. And this 60 cable theory, where one has SG2 gauge theory coupled to tensor multiplet, and then SG1 gauge theory, which is just tensor, and then these bifundamental vectors together, they are trivial to each other. And this can be seen explicitly by compactifying one of, say, word volume direction and trivial, then this becomes O5 minus, care of O5 minus, then you can do SDR, then it becomes N0 ring M, which again, Ami Hanai told us how to do it. Then it gives us a detail of the break pictures, so one can show the triviality goes very well. So one can test this kind of calculation by calculating elliptic genus of the partition function of this case. So there are two gauge groups, so there are two types of instanton strings. And then here we have a lambda instanton strings. And then there is a fractionalization of the momentum due to this non-abelian gauge theory. And the fractionalization of momentum and this multiple string structures are extending each other. So there is sophisticated map between winding string numbers and fractionalization, momentum, and so on in two sides. So that's what we have figured out. But this is of course what is expected, and this is just a volume of exercise for more challenging problem, which we are working on, which is E6 case. E6 case, A-type cable theory, E6 case theory with tensor, then SG3 tensor. Now, elliptic genus of this one is again extremely hard, and Sokkin managed to produce in general formula. One of the reasons is that naive instanton string dynamics on SG3 with no flavor generates anomalous to the field theory. So you have to learn more than to make things to be constant. They managed to do that, but I don't think they managed to do for E6 case. However, trivial version of it is extremely simple. So here one can calculate the partition function rather easily. So with because you can do an easy calculation, here things are much more difficult. So using this trivial, one can figure out the partition function of E6, which Ami did for Hilbert series, but not the generic continuous. So part of it has been done by Lockhart and Del Giotto, which maybe we'll hear about in next week. But and so there are E7, E8. So there are a lot of work we can learn from this kind of exercise, and this is one of the research direction we've been working on. So instantons and instanton strings, this is a tip of iceberg. There are a lot more structures, and there are many different ways of approaching it using topological string calculations, and there are other approaches. And that have, those exercises have told us a lot about the 5D and 6D conformal field series, and hopefully in future there will be more stories to be told. Thank you.
Any questions? So, I'm a bit ignorant on kind of what the state of the art is in terms of understanding these N=1 little string theories. Is there just a zoo of them that we don't really understand? We don't know
Right, so,
about? Or?
right, so question is, what's the interesting part to look at?
Right.
What's the interesting so and partition function is one of these probably something simplest quantity to calculate. Maybe there's something called the DACQ of little strings, and then there's various when you can stack up a lot of for example strings, and then this will deform the geometry. There's ABCD stories. There are a lot of other stories haven't been explored yet, and so state of art I think is the current challenge is there are very non-trivial but obvious part of the linear string theory, and we don't have a strong control on the part of components. So,
I'm sorry.
for example, E6 case, we don't have a continuous calculation except a single string. We don't know what to do. Even this triviality is not fast enough to product by the order. So there are a lot of things like that. So there are theories, you want to touch it, and but you just touch the surface, you don't know what's in there. So, and then there are some strong men come with extremely non-trivial technology to write down the answer, and so on. And also there are a lot of mixing going on here, and that will teach us about new things about conformal physics, where we don't know how to. So this is part of the exercise will teach us about superconformal physics, and also people haven't calculated the index function on S1 plus S5. We have started the for 2-comma series, but still we realize that our technology is not strong enough to resolve the certain ambiguity. So 1-comma theory we are trying, but the same issue will be there. So we are putting this and that and trying to put some hands on it.
So let's thank Kimyeong.
Thank you.